Welcome to today's webinar, everyone. It's Designing for RF, Tips and Tricks from the PCB Design Pros. My name is Brittany Wegman, and I will be your moderator for today. And before we get started, I'd like to address a few logistics and details on the GoToWebinar platform. If you're unable to hear the presenter or see the presentation at any time throughout the webinar, please let us know in the chat and we will do our best to resolve any issues. If you have any questions throughout the webinar, please type them in the questions panel as they come up. We will have representatives ready to answer your questions directly. This webinar will be recorded and posted on the EMA resource page. That said, I want to thank you all for joining us for today's webinar and introduce you to our presenter, Orlin Bates. With over 40 years of experience in PCB design, Orlin is a highly dedicated senior field application for EMA design automation. He will start off the webinar with an overview of RF design and some common challenges, followed by a brief demonstration. Assuming we have time at the end, we will field some questions in a formal Q&A. Thank you for your attention, and now over to you, Orlin.
Thank you, Brittany. I would like to introduce myself, Orlin Bates with EMA Design. I started out, my first RF design I ever did was hand taping using an X-Acto knife, and I can remember that engineer telling me the RF designs is the wave of the future. And we'd take those Bishop Graphics tape, trim off and respin the board, test it, go back with the X-Acto knife, retrims, do another spin of the board, go in the lab testing it. I would say, as of today, the future is here. Wi-Fi is just about part of all the products that we produce nowadays. The agenda today, we're going to talk about the Wi-Fi waves, design considerations, best practices, and in examples, I'll be doing some demos. And if time permits, we'll have some question-answer time. So what are RF waves? Radio frequency, the acronym is RF, refers to the rate of the oscillation of the electromagnetic radio wave in the range of 3 kilohertz to 300 gigahertz, as well as the alternating current carrying the radio waves. This is the frequency band that is used to communicate, transmit, and broadcast. The term microwave is a reference to a class of waves referred to as microwave range, or the spectrum of frequencies that the Wi-Fi signal actually operates in. For example, the Wi-Fi signal from your laptop is often emitting a 2.4 gigahertz, a frequency found within the microwave range, or the spectrum of 300 megahertz to 300 gigahertz. That happens to be the same frequency of our microwave ovens also. The wavelength as an alternating current depends on the frequency. In the diagram you see here, we have our magnetic field, the electric field, the propagation direction, which would basically be that radiation length, and that is measured in wavelengths. The distance between the Wi-Fi wave is shorter than that of a radio wave, but then it's longer than that of the microwave. That gives the Wi-Fi a unique transmission band that cannot be interrupted by other signals. The Wi-Fi bands are about 3 to 5 inches from crest to crest being the wavelength that you see in the diagram. Design considerations that need to go into effect would be health and safety requirements, those of the country you're designing in or countries you plan to sell your product in. Also in the States, state to state could have different health and safety requirements. Obviously, the environment conditions that it's going to operate in, you see the cell phone without its body in the background, but also environment conditions like the shuttle and the space station. Product life cycle, how long you expect that product to actually produce, last without being redesigned. So that life cycle is very important to take into account. Then most important would be the stack up or the material used. The selection and the consideration for those stack up materials are also very important. Under best practices, we'll talk about RF ground. And proper grounding is key. Connect the ground pins to the RF components and to the RF ground planes as short as possible. Ideally would be to put that pin out there and have a via right in that pin. So via and pin would be the ideal, the shortest possible. If the board includes multi-layer ground planes, provide many ground vias wherever the signal will actually transfer to one of the other planes you can never put enough ground vias in that area. The best practices, RF ground, and we can't say it enough, RF ground. To consider the use of the RF fence as a shield and a cover. In the diagram to the right, you'll see that we have a fence protecting that RF signal. When that metal pan is put down over place, it seals that off from the rest of the circuit. It isn't uncommon to have multiple fences on a design shielding each part of your RF. Shielding is what it's all about. Those vias in the ground plane is your best defense, and vias in the pad is what's best when you're changing those layers. Plating, we start off with our normal copper material, but the gold plating for RF components created from the etch is the best use. No copper islands should ever be near the RF circuitry. And thieving that the board house would want to put in there to keep that board from warping during fabrication of it should never be near any RF circuitries either. Grounding both ends of the copper pores and stitching as many vias wherever possible should be a priority. Separating RF planes from all the other planes is also a priority. Solder mask removed from the RF traces. So by having solder mask where the RF fields, that'll give you a better transmission. And if your boards are made by different fab houses, you get the most repeatable transmission from those boards by not having solder mask on top of your traces. Best practices for surface mount versus through-hole. Surface mount by far is better for the RF design. It would be better to never have a via needed in that circuitry. The only vias needed would be during that grounding process. So surface mounts lends to the best parts to be used in RF. But if through-holes are required, back drilling should be used. With a through-hole component and the vias, that back drilling will remove unwanted antennas. Stubs on the vias and through the hole pad stacks are just as bad as that copper thieving and those copper islands we were just talking about, because they become unwanted antennas. The best practices for stack up and material. Multi-layer boards work out best because you always want to have a continuous ground under all traces, more or less sealing off those traces, having ground on each side. Consider the material selections carefully. Standard RF may not meet your needs. Fabric weave in there does affect that signal. FR4 might be cheaper material, but to respect that wave and its requirements, the FR4 can fall short for many applications. Best practices on those vias. Using that isolated vias to separate portions of a filter or a matching network. Use at least number of vias you can when routing that RF signal, but use the max number of vias for that RF grounding. Vias are shielding, and this is our number one requirement, shielding and grounding. Routing, orientating a sensitive trace orthogonal instead of diagonal works best. Using the short traces between the crystal and the RF device is also your best practice. Softwares that will allow you to allow the pad to touch and make connection is the ideal software for RF routing. Keep interconnect traces separate as much as possible and keep trace lengths to a minimum. Best routing practices, adhere to the proper cornering and routing. Use the wire-wound inductors whenever possible and avoid using printed down circuitry parts unless they're needed. Placing inductors, coils, and planers, isolating them from each other is best practice. If inductor, planer, or coils are created from copper becoming parts, grounding and shielding for isolation is a must in this area. Best practices would be to simulate. Simulation is strongly recommended. If RF components are being printed down as part of that board, simulation should be a requirement. Any serious RF design should be simulated. We interface with those simulations with IFF files and DXF files. We do not simulate, but we interface with those simulation tools. The key takeaways here, ground, ground, ground. I cannot say it enough, ground. Carefully consider RF implementation as design choices. it has a significant impact on the cost and the complexity of your designs. Understanding the effects of RF circuitry has on the rest of your design is half the battle. The real issue will start when you have an RF circuit that needs to be added to that digital design that's already complete. They do not get along. So grounding is your best defense against that battle, and then simulation of the entire board. So at this point here, I want to show how we could get some of those components. In this case here, you're looking at a fence that I'm creating. And the reason I create the fence as a logic symbol instead of a mechanical, even though it's a mechanical part, is I want to go ahead and get my ground vias in there. And I can go ahead and open that up, create this symbol, make it electrical. That way I can go ahead and tie my RF ground to this frame that I'm going to set down. And then you can see my vias already placed in there that will be connected to the plate there. This shield's going to cover up the parts. But at this point, I want to go ahead and demo how we would bring in a new one. So let's go ahead, or at least make a modification and take this triple crown. So here's a component that's already been made, but a change is coming in. So what I'm going to do is go ahead and bring in the change using the DXF. And I need to go out and find my file that was sent to me. And I'll get the triple crown. And a change has been made. And since a change has been made, I'm going to do an increment addition to this, meaning I'm leaving what's already there, bringing in the change. I want to be able to view what has actually happened to this device since I've used it last. If I was building it from scratch, I wouldn't hit incremental addition, and then it would be a brand new part. And of course, I need to map the layers, so I need to go ahead and select all the layers, and it's already set up for class and etch top, so that's fine. So the class and the subclass is already set, so I can just say OK to that, and actually bring that DXF in. So as it imports that in, it's going to overlay it, and I can see the differences. There pops up my log file, so I can read my log file on everything that's happened. And red shows the new changes that's come in. It's slightly changed a little from what was already there. I would go in there and remove the other layers, or just go back and rerun this and not increment and create a whole new symbol, possibly just triple crown Rev 1 or Rev 2 on this. So that's how you would bring a symbol in from your simulation tool if they've already built a divider like this, and you wanted to bring that in from their tool. You could bring that in, create that. Now that's a symbol, and it's a symbol in etch that you can use. So I'm going to go ahead and open the board that we're going to use that on. I won't save that. Change this over to the .brd, and we'll go ahead and grab this splitter board. Now with the splitter board here, you can see that I've already got my component in here placed. And what I wanted to do is go ahead and zoom into that. Oops. One thing I wanted to point out is if you look in the upper left-hand corner, you'll see I'm in the PCB, OrCAD PCB Designer Standard. We'll be changing licenses later on, but I'm starting out as standard. Standard is fine for building symbols. And I can design any board out there with standard. It's no different than the hand taping days, but it doesn't necessarily mean I want to. There's a lot of work that I would have to do in standard that the other tools allow me to leverage the software to do the work, and I don't have to do that work. But in the case here with embedded components here in this splitter here, I've got a component in here. Let's go ahead and turn the find filter on. I want to identify my shapes there. And I hover over this, and you can see here I've got a boundary in here. I've got an embedded cap. Now, standard doesn't provide you embedded parts, but our software allows you to create subclasses as you need them. You can create as many as you need. So I go in there and create a subclass called embedded, and this is my capacitor or resistor, CR1, and then I can have CR2, and I can have CR3. Those are the different subclasses I've created. I can create those devices in there for the embedding, even though the software doesn't make it easy for me to do. It doesn't prevent me from doing it, and that's the important takeaway there, is the software will allow you to create, as I say, design any board out there. It's just easier with some of the other higher level software. So I have those embedded parts already in there for my divider. And that's about all I could do in this without doing some extra work. So if I go in there and I start making my shapes, you can imagine drawing these shapes, and that is, again, the preferred cornering for that shape on the reflection back off of that. So that would be what I want. But I know the higher level software will let me do far more in that. But before I leave this, I want to point out that here's the schematic for that. Let's go jump into, there's the design, and here's the page, and here's all my RF splitters, the dividers that I have in there. They are symbols in my schematic, so because I've created them as a symbol in the printed circuit board, the schematic can drive those symbols even though these symbols are printed down instead of purchased parts. And then it just becomes a no pop in bill of material. There's no parts to really populate. Their circuits are printed down. So at that point here, I want to go in, we talked about putting a via in pad. So if I'm going in there and I want to do my connection, I can go into here and click on this, and I can do a right mouse button, just say add via. Our software is going to allow you to add that via right into the pad. That's the best connection that you could possibly make. RF boards are expensive, so that cost of plugging that via is not that big of a deal in the overall cost, but performance is more important at times than cost. So the software will allow you to put that via in pad. So with that, let's go ahead and shift now. I'm going to come in here and I'm going to change my editor. And instead of having standard, and there's my professional, the next level up that allows me to do other functionalities above standard, meaning the software is doing the work and I'm not have to. I want to jump all the way up to our Allegro PCB designer. And then I'm going to go ahead and turn on that RF option that we have there. And I have high-speed miniaturization. There's where I could do my miniaturization instead of having to do it manually and do a lot of fab notes. And then we have this Allegro toolbox I'm going to turn on. That will help me do some things. Now what I want to do is go back to Pro Productivity Standard for a minute and notice that these gray away because those options aren't with Standard. For that matter, they're not with Pro either. But our Allegro Productivity Toolbox is with the Standard and will run with Pro. And there's functionality in this Productivity Toolbox that will allow you to do RF designs maybe without having to go to the price of this license here with RF. So you can keep that in mind. I'm going to go ahead and turn those options on, and I'm going to say OK. The screen's going to blink because it's recalculating, and now it's loading in basically my new commands I have with the higher level software. But notice the design hasn't really changed. We're still in the same design. What I want to do now under RF is go in there and start making a connection. So I'm going to add a connection in my RF, and I know that these two need connected, and I'm going to be on the top layer doing that. I will hover over this pin and do a right mouse button and just snap to that pin because I want to make sure I connect to that pin directly. And then I can go in there and start routing. Now, as I'm routing, notice on the right-hand side, it's actually keeping track of the physical length. That becomes important if you're having real high speeds because you need to match those lengths of your signals. Basically on like the backplane I'm going to show you, that they're all matched lengths, so it becomes very tedious that the physical lengths match. It also lets you put in your working frequency in here, so you can go ahead and change your working frequency in here. The miter fracture that what you've got set up, so you notice that it's mitering the proper way or what is best practices there. So I can come in here and I can do a snap to pin and I can lock right back on that pin like that and then be done. And then I've got that trace in there. Now what I want to show you is the fact that I do have a plane in there. There's my plane on the right above S1 and my plane right under S1. So I'm shielding that really good. But what I also need to do is go in there and add those vias in there. It's important that we go ahead and shield this like I was saying. Now, in standard, I'd have to do that all manually, but here we can go in and do a place a via array. Now, a matrix is what I'm going to use, but boundary is what I use to create this part. This is what's considered boundary, and I defined what it was, and it put those vias in automatically. Now we're going to do a matrix. I go under the Option tab here under Matrix, And I make sure that I have enabled the DRC checking. So if it creates a DRC, it'll remove that via from there. I don't need to do it. I'm going to go to shape mode because that's what I want to do. The net is going to be ground. And this pad stack is this via 1 through 4. It's a 1 through 4 board. It's a 16 pad and an 8 drill on there. I'm telling it to stagger, and then we're going 25 and then 25 horizontal and vertical. So basically, all I have to do is come over and click on the shape that I want. It's going to go out there and calculate. And what you're seeing is a highlight. This is a preempt of what's going to happen. If I click on that shape again, it's going to set these all down. When it sets it down, it'll immediately go into a DFM check to make sure there's no DRCs that's being created in there. And it'll remove those vias that creates it. So you can look in there, and some of those vias looks like they're going to be right on top of my etch. But it would remove those. If I click on that, it's going to take a little time for that calculation. So at this point here, I'm just going to cancel out of it. But the second click would set it down and remove all those DRCs. Let's go back, and we want to do, let's say, a component placement. So I've got some components that I've already built, and we're going to go in there and add a component. And I can go in here and decide whether I'm doing the micro strip or if I'm in there and doing a strip line. Notice that strip line's grayed out. It's because I'm on the top layer, so I have to do a micro strip. But I want to come down here now, and I want to find a part to add out there. So let's find my surface mount, this inductor here. And here's my inductor. It's already created. I can click it once, and that's where I'm going to place it. But now it's letting me decide what rotation I want to put that on, whatever increments I've decided to lock that in on. And then there's the component. The other thing I can do with this, let's go ahead and just set one out here and say done. The other thing I can do with this software now is I could go in there and edit that. And I can say, I want to go in there and scale that. And I could grab this component to scale it. And I've scaled it to a 0.5. Notice how the coil has come down. Now, if I want to go ahead and change that to a 1, 1 might be the actual size. It is. Let's go 1.5. So I can scale that up. And I'm telling you, this is a lot better than taking there you notice I scale at 1.5. This is a lot better than taking an X-Acto knife and trimming or trying to recreate a part that you had to do in the old days. So we'll cancel out of there. Some of the other features that RF option is going to give you is let you convert. So I can take these are components I placed, RF components. I can take these components and I can turn them back into shapes. And I could modify that shape. Once I modify that shape, I could turn that shape back into the component. So although it's a component and was built that way, I can turn it into a shape, edit that shape, and turn right around and make that shape back into a component, allowing me. If I do my C-lines, connect lines, or copper lines as some people want to call them, which what I have right here is just a regular copper line instead of a RF routed shape, then I can go in there and I can take that C-line, turn it into a T-line conversion. Basically, I'm going to turn that C-line into a shape, and it would be a shape for me. Now, it's not cornered properly. I'd have to go in there and trim that back using my electronic X-Acto knife, trim that corner off of there. Or I could just go in there and start routing, which would be easier. And then here's that IFF interface I told you about. The nice thing about that is it lets me export out. Being able to export that out, I can load that into those simulation tools, and we can do all kinds of simulation on these designs that you need to do. Again, any serious design like this, you need to simulate that. So at this point, I want to go ahead and shift gears. I'm going to go ahead and open, and we're not going to save what I did there. And at this point here, I want to go ahead and open this RF open mask board. If you remember during the slides, I was telling you when you interface and you put that digital board out there and you bring in your RF in, there's where they just don't get along. So on the right-hand side here, I have my RF trying to interface in with that digital world. But what I want to do is go ahead and grab visibility, and since I've already set my views up in here, the nice thing about it, I can set my views up there where I'm working, just click on the view. So here's some parts that I was working on. What I really want to work on here is to show you, again, I talked about that Allegro Productivity Toolbox, and I'm going to use one of the functionalities out of there. So I'm going to go over under my edit command, and cross copy is there. And the nice thing about cross copy is it's going to let me go in there, and I'm going to decide that on the board geometry, I want to go ahead and do a solder mask top opening, and I need to do that opening for my RF circuit. Like I said, it's better to have that open, more consistency. It's going to be gold plated, so it's not a corrosion problem. I can click on that, and notice what it's doing is it's literally creating. I'm going to go ahead and do the pad, even though that pad would already have a solder mask opening. I'm going to go ahead and do it so that it creates it basically on that board geometry solder mask top. So when I create my artwork, all I need to do is turn that layer on, and I've got everything, pads included. But what it did is let me cross-copy those items over to that solder mask opening. Now this RF trace through here has solder mask opening on there. Again, more reliable, more consistent if you're crossing over to different. So at this point here, I want to go ahead at Fab House. Now, because I showed you with the Allegro Productivity Toolbox that cross copy, I also want to go in under routing. Another option that comes with that would be the coil designer. So I'm going to go ahead and open up the coil designer. What's nice about this is it'll let you do the round coil, rectangular, your octagon, and your hexagon. So whatever coil you're creating, it lets you create the turns. It gives you your overall diameter and the X. It lets you decide how wide you want that copper trace to be, and then the spacing on that, rotation on that, whether you're going also clockwise or leave it and it'll go counterclockwise. So at this point here, because of all these values I set in there, out on my cursor now is this coil design. So I can go ahead and place that and set it down. Now I have it out there. I can modify that, but it'd be obviously easier to come back in here and do it in this area here. Here it is as a rectangle. So what this is doing is giving you the power to do certain coil designs, planar, inductant designs that you want to do right in copper when you need to, without really having to get the RF option. But again, you saw where the RF option does help. You can expand these as you need them. We'll say okay to that. There's the parts there. Now, I also want to talk about the back drilling, because I said if you're having to use through-hole parts, that's very important. The back drilling, get rid of those antennas. So I have another board for that. Let's go ahead and let's not save any of that. So I have it for the next demo. And then I'm going to jump into this 50-layer back plane. It's going to take a little while to load. There we go. So let's go ahead and see if my my visibility works for this one. Yes, it did. Fine. So this is that high-speed backplane, and since it was running at such speeds, everything had to match. So as you can see, all these RF traces are in here, and they're tuned, and they're matching in the actual length, flight times that you need in there. But in there, so I wanted to talk about back drilling. So we'll pop up here to manufacturing. And what I want to do is come down in here, and we want to look at the NC, and we're doing the back drilling setup. What I like about this in the back drilling setup is the fact that it goes in there, and I can go ahead and decide what layer I want to start back drilling from, the bottom, and the objects I want to hit. So it would be pins or vias or pins and vias. And then I want to go in and say to what layer that I'm back drilling to the different layers, and must not cut layer, where I want it to stop. There's where my traces are. Cannot cut off this layer without opening up my signal. And then it's automatically going to create this depth drill for you. The nice thing about that is by creating that, it creates the NC drill file for the fabricator. So you're not in there like you did in the old days having to figure out, or in most cases, people threw it over the wall and let the fab house try to figure it out, saying, I want back drilling, and then they had to figure out how deep they had to back drill. Again, the important thing is making sure your stack up is correct. We want your stack up to be correct. This is what it's basically running off of, is that stack up. And then it creates those files for you automatically. That's part of the benefit. If I was doing this in my standard, I would be doing all this stuff and calculating it myself and doing fab notes to cover everything that I was trying to do. The other thing I would be doing, let's go ahead and just cancel out of that. Let's move down here. I don't have it turned on, so let's just go turn everything on at this point. I've got everything turned on. I'll apply that. So what I've got here, if you notice, is the actual drilling information that the software is doing for me. I'm not having to go in there and create these. It's doing it automatically and putting it on the layer I want. So here's my back drill from bottom to layer 9, and it's going to use this as the figure, and then I can turn that layer on, and that becomes one of my multi-sheet fab drawings that I would have out there. If I go ahead and expand this view, these views are custom views that I've made, but these views here are my films, and in my films, there's where I've got the different back drill layers called out in that fab drawing so that the board house is able to use that. And again, it creates all those, usually stacks them right on top of each other, and I go in there and separate them because I need that visually to have them separated. It's more my benefit than it is anyone else's. The other thing I want to talk about was, because we were talking about stack up, so let's go into the stack up here. And here's my stack up of my 50 layer. And what I'm able to do is we can import or export this. So I could create this stack up, export it out, IPC 2581, or a cross-section technology file or HTML file, and then I can have the board house check me. But if the board house comes up with all this information long before I ever start there, and they say this is where the signal should be run, and this is where you have 100 ohms impedance on there, they do all that calculation for me, select the material. In this case here, notice I'm not FR4 because that's not the material used. But I can import that from an IPC 2581. So if the board house has done that work for me, I'm not taking my time to go in there and drill down in and have to create all this stuff. I just load it in, and my stack up then is exactly what the board house has me set up as. And one other passing comment, under signal integrity here, I can go in here and I can do edge to edge, and then it's going to go ahead and calculate what my differential would be on single and for differential pairs. What it's using is calculator. Cadence decided not to reinvent the wheel and develop it on their own. They just licensed Polar to run in here. Polar is what most fab houses use. So when I start changing my values in here for my gaps and my line width, then I know my single impedance, what I'm getting, is correct. So I don't have any issues there. So let's go ahead and just close that out. I'll cancel that. I'm not changing that. So again, the length issues that I might have in there would be solved because the RF traces is actually keeping track of those. So that concludes the demos that I had. So I'll pass this back to Brittany now.
Thank you, Orlin. And at this time, I would like to open the floor for the Q&A. Please enter any questions you have in the chat now, and if we're unable to address your question immediately, we will be in contact with you. Just a reminder to all attendees that this webinar will be recorded and posted on the EMA website within the next few days. And Orlin will start off with the questions with this one. It's, can you share best practices for printed antennas?
For printed antennas, yeah, in most cases, the biggest problem people have was not clearing the area for that antenna. So you absolutely want nothing on any of the layers where that antenna is printed down. So all layers underneath there should be cleared out. And then a ground shield obviously around that antenna. But the antenna is always best put up in some corner as far away from all other circuitries as you can get. Sometimes that doesn't lend itself to being the best practice because of the way the shape or the form factor that you've got to fit into. But be sure to not have any components underneath that antenna, any circuitry underneath there. Once that antenna is printed down, make sure it's wide open on all layers underneath that.
All right, and next question here. How do different frequencies affect RF circuitry?
So a lot of that frequencies, back to that first slide where you actually notice those propagation, or what's called radiation, how far it passes out. So those frequencies increasing or decreasing can change that wave on you and the propagation on that. So in most cases, when you're doing that design, you would have a spec for whatever you are designing, unless you're out there creating brand new. At that point, there's where you're going to rely on your simulation tool the most, changing those frequencies, simulating that, and seeing if you have a dB loss on what it is.
All right. Somebody else is wondering, what was the reason for keeping traces void of the solder mask?
Again, it's that fab where you go out with the fab. You get a better transmission of an RF signal without having solder mask over it. Solder mask basically is a coating over that. That coating is usually cheap, liquid, imageable material, so it's basically squeegeed onto your board at different thicknesses. You can't really control that thickness, so in some areas that could be thicker than other areas, and that will create problems in that transmission. So it's best practices just to open that up, gold plate it, and when I say gold plating, usually people cringe. Yes, it is expensive, but they have emission gold, and they have gold where they're just flashing it, and it's not as expensive as the gold plating from the 70s and the 80s that we had to use. But you get a very reliable signal that way, and that's really what you're after. But that reliable signal then has to be controlled. That's why the shielding becomes very important, because now you've got a good, strong signal, and now you need to control where that signal is going to be headed.
Okay, and somebody else is wondering, does a shield have to be a physical wall?
No, and it really depends on the product. Does it have to be a wall? No, but in cell phones, I would say yes. So it's the product that really drives what type of shielding you're going to do. A lot of times that antenna we were talking about, you can just shield it with ground traces and vias. But in the case of a cell phone, you know, if you ever tear a cell phone apart, you'll see there's all kind of little shields all over there. And again, it's the product that drives that. And that product is driven by failure rate, what's acceptable in medical equipment. I mean, RF design's been used in medical equipment for over 75 years. Failure rate in medical equipment isn't acceptable, especially when it's in an operating room.
Good to know. And Orland, can you describe the best way to handle net shorts across the RF components?
Yeah, well, our software allows for a net short, so it's a property that we put on there, and it just allows us to short the two nets together. If you're in there actually using the RF tool, when you're going across there, it allows you to go ahead and join the different ones. In the case of my divider there that you saw that I was building, there's a case where I'd use the net short because I'm driving it from capture, not the HDL tool. So I got to handle a little different with capture than I would with the other tool. But that net short works fine in that area.
Okay, they're great questions, guys. Keep them coming. What should be the ideal trace width for a high-frequency transmission?
And that, I would have to have you go back to your simulation tool, depending on what frequency you're wanting. In the example I was showing, I was running a 16 mil wide trace, but in other designs, like that high-speed backplane, I actually had a 20 mil trace. But all that was really defined and finalized through that simulation tool that we were using.
Let's see, next question here. Any impact off of the via diameter hole for the RF?
Well, in most cases, I like that via in pad. So the diameter for that, or the ratio basically for that via, doesn't lend itself to be a problem if you have the luxury of putting that via in pad, which would give you the best signal quality that you want. But the ratio of hole versus pad, that ratio is no different than any other digital board when it comes to RF. What you do have, though, is that stack up, and that's the back drilling I was talking about, because you do not want an antenna in there. And, you know, if you have a pad and you're going to back drill, obviously you got to back drill that pad out of there. So you're back drilling a much larger size. And although I didn't demonstrate it, our software shows that in a good graphical way that defines your size of your back drill and defines the pads that you're trying to knock out of there. So best practices really would be following the normal IPC standard for pad to hole ratio. But again, I really would stress putting that via, and then you don't worry about the pad, into the pad of the device itself.
Good to know. All right, our next question here is a little more OrCAD specific. They were wondering if OrCAD has a built-in printed antenna that's a design tool. Specifically, they're looking for a Wi-Fi antenna.
No, to my knowledge, there isn't one in the library because OrCAD library really wasn't geared for RF. If you notice when I was demoing and I was looking for my coil, there's a lot of symbols in the RF. Now, if you move up to Allegro and get the RF option, obviously you'll get that whole library of parts. But in most cases, those parts are built, you know, either from a vendor spec, if you're going to use that, and if you're printing it down, you can still get a vendor spec on how to print down the antenna that you're wanting. But with that comes some purchased parts that goes along with that antenna. There was a few I've done, and I've just followed the vendor spec on printing down that antenna.
All right, and next one here, Orlin, in your experience, what is the best practice to reduce noise in amplifiers?
I'd have to lean back to that number one again, is shielding. I mean, you can't, again, we stress it a lot, but you can't stress that shielding and grounding. And then a lot of times, not just, you know, if I'm in there shielding and I find extra noise in there, it never hurts to put caps or ferrite beads in there so you could always grab those. I mean, the pads are cheap. You don't have to necessarily put the parts down, but it's really nice once you've fabbed that card to have that ability to go ahead and add some capacitance in there, or go ahead and add a few ferrite beads in there that you might want to control that. But ground.
Yes, very much so. And actually, we have a question pertaining to ground. Somebody says, does thickness of the ground plane make a difference? For example, is the thicker the better?
I've actually found in the simulations we run that it does not. The thickness doesn't. The fact that you have continuous ground and no breaks in that ground is more important than whether you have a 1 ounce copper or a ½ ounce copper. So in all the simulations we've done, we've actually went up to a 2 ounce copper plane. It doesn't do a thing in the shielding. It's really the 1 ounce, 2 ounces current. I mean, that's really why you would go to a thicker piece of copper, is current carrying capability. So the current you're driving through that plane is more important than, once it's copper and once it's a plane, it's a shield. It shields and it shields good. Add those RF vias in there.
All right, and these are great questions, guys. I think we're going to do 1 or 2 more, and then we'll wrap it up for today. What factor determines antenna efficiency when selecting an antenna? For example, is efficiency or gain more important?
Well, with that, since I'm the layout person, I would go back to my double E and ask the double E that very question and say, this is out of my realm. You tell me what you're needing so that I can go in there and lay it out accordingly. So that's really a question I would take back to the double E, the RF engineer, for that. It would always hinge on the product. It would always hinge on, you know, I mean, the difference between a remote control that's going to open a garage door and a remote control that's going to turn your thermostat down is far different than those remotes that you're using, you know, if you're sending a signal out in space to talk to the space station, you know. So it's really productivity in the product that you're doing. So what you're actually designing is the dictator on that, and that's where I'd have to come back to that RF engineer to say, you need to tell me what I need to know in this area.
Okay, and we'll do one more question here. What are some of the differences between RF design and high-speed signal trace design for protocols like SATA or USB?
Well, like the USB, you're really sending that signal through the printed circuit board, and it's more of a digital signal. The RF, really, although we're printing down some RF signals, we're still sooner or later going airborne with that signal. And in the USB, you're plugging a device in, or you're plugging a cable in to go to another device. So the realm of USB versus the realm of RF is really that airborne signal that you're transmitting out into the open air for someone to receive. So that would really, the USB would really fall under the regular digital, 80 ohms match length, plus or minus on the USB. Just no different than the way we design DDR 3, 4, and 5 in the memory. That flight time from the driver to the receivers is what's important. But again, that flight time is all in the board, and RF is we're sending that signal out into the air.
Awesome. Thank you, Orlin. And I believe if you're still interested in high-speed design, we should be having a webinar coming up within the next couple of months here on high-speed design. So stay tuned, everybody. Looks like we have a bunch of questions still coming in. Unfortunately, we're out of time for today. However, if anyone has questions that were not addressed during the webinar, we will be following up with you on an individual basis. I'll be closing the webinar now, and we'll be sending everyone a recorded version of today's webinar on the slide deck within the next few days. Thank you for taking the time to join us today, and have a great day, everyone.
Thank you, Brittany.